In this video, we're going to be taking a look at the history of the model of the atom. We're going to start by exploring some background information regarding the electromagnetic spectrum, and then afterwards we're going to connect it all to how we jumped from the Rutherford model all the way to Bohr's model, and then from Bohr's model to Schrodinger's quantum model of the atom. So essentially in the first video, we saw this first chunk of the timeline as well as some early philosopher ideas. In this video, we're going to be focusing on planetary and quantum model background information first, and then we're going to jump into those models. You do need to have some background knowledge on electromagnetic radiation to fully understand the brilliance behind Bohr's model and Schrodinger's model. So I need you to get that light is a form of electromagnetic radiation, which essentially means electric and magnetic fields that travel as waves. So light travels as a wave, as you can see in this image over here. And waves have different properties or characteristics. One thing you could measure on a wave is its wavelength. So the distance from one point on a wave to a similar point on that same wave, this is the wavelength over here. This is another example of a wavelength over here and over here. This is a long wavelength, this is a shorter wavelength, and this is an even shorter wavelength. You can also take a look at what's called frequency, how many times a wave passes a point per second. So let's say this is a 1 second time strip here. You'll notice that this wave does not repeat as often as this wave. This wave repeats quite a bit. So this has a very high frequency. Low frequency, in between frequency, high frequency. And another thing you'll notice as well about electromagnetic radiation or light is that there's many types of light. We organize them based on their frequency and wavelength over here. There's gamma rays, X-rays, UV, visible light, infrared, and radio waves. And that's what we call the electromagnetic spectrum. It's a range of different types of light based on their wavelength and frequency. You'll see that a very small section of the electromagnetic spectrum is visible light. That's the light that you can see. So the light from the sun or from light bulbs is white light. It's actually not really white. It's made up of different colors, these different colors here. And evidence of that can be seen when you put light through a prism or when it rains and you see a rainbow. The white light goes through the raindrops and bends at different angles and causes the different colors to separate enough so our brain can see them. But that's the idea behind the electromagnetic spectrum. There's different types of light that exist on it. There's only a very small segment that we can see, and it's called visible light. We can see that more effectively here. So this is our electromagnetic spectrum. You can see that we have different types of light based on their wavelength and frequency. So small wavelengths here and increasing wavelength as you go this way. Gamma rays, X-rays, UV, and then we get to our visible light portion over here, which is between the 400 nanometer to 700 nanometer range. So that's the measurement of the wavelengths for the visible spectrum that we can see. There are some important relationships I do want you to know as well. Firstly, I want you to understand that most light is actually invisible and only a small segment of this spectrum is visible to us, to our brains. The other relationship is the relationship between wavelength and frequency. So let's go back over here for a second. You'll notice that this is a long wavelength. This is a short wavelength. Try to come up with a relationship between wavelength and how many times it repeats. So the longer the wavelength, the blank the frequency. Would it be a lower or higher frequency? Or the shorter the wavelength, the blank the frequency. Would it be a lower or higher frequency? So as you probably noticed here, if you have a short wavelength, there's a lot of repeating. The wave repeats on itself in that second a lot more times, many more times. So a small wavelength or a short wavelength, high frequency. A long wavelength, lower frequency, doesn't repeat as often. So we say the relationship between wavelength and frequency is inversely proportional. The wavelength and frequency are inversely proportional to each other. In other words, as one goes up, the other goes down. So a higher wavelength means a lower frequency, right? Higher wavelength doesn't repeat as often as the shorter wavelength. As you can see that here, shorter wavelengths repeat more frequently than longer wavelengths. Now, the other relationship that exists is with energy. wavelength and energy are inversely proportional. In other words, as one goes up, the other goes down. So what that means is this has less energy than this, right? The longer the wavelength, the lower the energy within. And you can kind of see that visually. If you have short wavelengths, you just have more repeating of that wave within that 1 second frame. The longer wavelengths, you have less repeating happening. So less energy in the long wavelength, more energy in the shorter wavelength. If you look at our electromagnetic spectrum here, what that essentially means is that gamma rays have the highest energy because they have the smallest wavelengths and higher frequencies. And things like radio waves have the lowest energy because they have the longer wavelengths. So if we look at this image here, we could predict which color of visible light has the most energy. Try to make a guess, try to justify it. So the color of visible light that has the most energy is in this region here, the violet region, because it has the smaller wavelength. The color of visible light that has the least energy, smallest amount of energy, is this color here in the red region because it has a longer wavelength and a lower frequency. Remember, a longer wavelength means lower energy because they're inversely proportional to each other. We're going to connect this to atoms shortly, but this is our first background information needed. Here are some more images of the different colors of visible light. You can see they differ in their wavelength and frequency, with the smallest wavelength being in the violet region here and the longest in the red region over here with the smallest amount of energy. Scientists study light in a tool or a technique called spectroscopy. So they analyze light using a technique called spectroscopy. And one of the main foundations of spectroscopy is that we take a white light source or a light source of some sort, and we put it through a prism, and you can separate the light into its colors. And so here we can see what's called a continuous spectrum. It's the white light separated into all of its colors along this nice smooth band from 400 to about 750 nanometers. So from that blue-violet end here to the red end over here with the lowest energy. So this is a continuous spectrum over here, which is the spread of the white light separated into its colors using a prism, some sort of piece of plastic or glass to do that. So what did scientists do with that? Well, we could take a chemical, for example, heat it up, put it into a flame, and then aim the light that is produced from that flame and that chemical through a prism and see what colors of light come out of that. That's what scientists noticed. They noticed that whenever they put a substance into fire or even electricity, it would spit out different colors of light, and you could get this little spectrum over here that would correspond to a specific chemical. It was almost like a barcode for a chemical. So these are spectral lines developed through experimentations by Kirchhoff, who was using Bunsen burners and heating up substances, and then seeing what colors of light would be spat out through the spectroscopy technique. So just to further elaborate, there's different types of spectra you can study. If you just separate white light through a prism, that's called a continuous spectrum. You just see all the colors of light there. Now you can also see what's called an emission spectrum or absorption spectrum. It depends on what you want to study. An absorption spectrum, you'll notice, is just a continuous spectrum with some lines missing. And that's basically because the substance that you shine light through absorbed some colors of light. So if I take some white light and put it through a substance and then through a prism, I'll get a spectrum, but it won't be it won't be a full spectrum because some colors will be missing, and the colors are missing were absorbed by the substance in this cool gas, for example. So I know that whatever the substance was in here absorbed these colors of light. You can also take a look at what's called an emission spectrum, where instead of seeing what a substance absorbs, you could see what a substance emits or releases or spits out. So these are the different colors of light that this gas spits out. And the really cool thing about that is you can come up with what's called atomic spectrum or atomic spectra or emission spectra. So you can take an element and you can give it some energy and then see what colors of light it will spit out. And what scientists notice is that different elements spat out different colors of light. So mercury spits out some light at this wavelength here, this wavelength here. These are wavelengths at the bottom, by the way. This wavelength, that wavelength, this wavelength. Every element has their own sort of unique barcode, and you could actually use this emission spectrum barcode to identify what element you have in a particular substance. So the idea is you heat up or give energy to an element by heating it up, putting electricity through it. Then the element spits out some light, and you get these different emission spectra or barcodes to identify what element you have. So they call that atomic line spectra. They're also emission spectra because it's about what they spit out, what they emit. Here you can see a few examples. This is hydrogen gas in a tube, and we pass electricity through it. And when it does that, the hydrogen will spit out different colors of light at these regions here. So as soon as I see this barcode with corresponding to these regions in nanometers, then I know I have hydrogen. Or if I see this barcode corresponding to these regions in neon, in the emission spectrum, then I know I have neon, for example. And so scientists were able to do these experiments and develop barcodes for a whole bunch of elements and substances like that. And again, we can see some more images of that over here, that each element has their own barcode. Scientists will study composition of stars, for example, using this technique so they can see what was absorbed or emitted by substances within a star. And you don't have to memorize these, but do understand that you can, if I give you an unknown substance and I provide you with its barcode, and I gave you this over here, could you tell me what substance we have? So if I give you something unknown and it matches up with sodium, then you know that chances are that unknown substance probably has sodium in it. So now we'll take a look at how this all connects to the models of the atom. Remember, one of the most important things to remember is that Rutherford's model, the main problem with it is that the electron is orbiting around the nucleus, and so it should be losing energy as it's doing that. And if it's losing energy as it's doing that, eventually the electron should, collapse into the nucleus. How do we solve that? Well, Bohr took some ideas from a few scientists. One idea that Bohr took is the idea of these emission spectra. Bohr tried to develop a model to explain the emission spectra, so we'll see how that fits into play soon. And Bohr took some ideas from Planck and also from Einstein. So we're going to take a look at what those ideas are, and then we're going to fit them into his model. So in the next video, we're going to take a look at Planck's idea of the quantization of energy to modern physics. We'll take a look at Einstein's experiment with the photoelectric effect and how it was how we applied Planck's idea to light. And then we're going to take a look at how those two ideas plus the atomic spectra came into play to develop Bohr's model of the atom.